probably still know less about Southern Africa and West and East Africa. That's maybe something we could debate, but I think there's certainly an opportunity for more research in those regions. I was going to show a little bit more about Southern Africa. Although perhaps there has been less work, it's not to say there isn't active work going on. So there's a little bit more detail here. I won't, in the interest of time, say so much about here, but just to say that this Congo air boundary there's a lot of renewed interest in this feature as a driver and controller of variability across Southern Africa. So what I want to do now is talk about how those large climatic zones, if we look at the whole continent, actually translate into meteorological features in the synoptic scale and the fine scale. So there's a couple of images here. Unfortunately, the one on the left, I wanted to show this because it's kind of a classic from 1945 and from the Society's Journal, Quarterly Journal. It's reversed, so north is on the left. All my other figures, it's the other way around. But this figure was based on very far less information than we have. They had one sounding, I think. They had a lot of pilot balloon soundings. But this paper actually is still influential, and forecasters still use the principles in this paper. And it defined these zones, zone A, B, C, D. And the ITF here, if you can see that, about 20 north, this is the intertropical front, or discontinuity as it might be known. And so these zones are defined relative to that. And the intent of this paper was that the whole north and south, both seasonally, between the northern hemisphere summer and winter, but also on a day-to-day basis. And as it moves, these weather zones move with it. And so zone A is kind of characteristic of desert, very dry. Zone B may have intermittent behavior. Zone C is the main rainy zone, what you might call the ITCZ. And so there's an updated version of this from the Forecaster's Handbook, again, Andreas Fink. And the zones are again marked here. So in fact, this perspective of looking at these synoptic lines and considering the northward and southward shift of this system is still an important and valuable approach to taking a synoptic view of the meteorology. So now zooming down the scales, what does that meteorology mean in West Africa on the local scale? Well, everybody gets interested in West African squall lines. These are really dominant in the Sahel zone, so the band just to the south of the Sahara. And they do produce 90% of the rainfall in that zone. As you move south towards the Guinea coast, then maybe there's a larger contribution of rain from slower moving weather systems. But certainly these squall lines, fast moving systems, are extremely important. And they're very dramatic. They're some of the most severe squall lines on the planet. Here's a really lovely picture of the approach of a squall line from Francois Guichard. You can see quite a few things here. You can see the waves generated by the squall line and the representation of those into the cloud field. At low levels, you can also see dust being lifted, even though this is over quite a well-vegetated surface. You can see the orange dust being lifted. So that lifting of dust is an important indicator of the cold air, which is surging out below the storm in a cold pool. And then it's also an indicator of the gust front, which brings high winds. So this is one of our own experiences from the AMA experiment. So this was a SODAR. The instrument, actually, you can just see it in the bottom right there. It's little eggshells here. This is the SODAR. And the screen here are metal panels that we'd staked out with guy wires and things around it. And so this is the effect of a squall on one of our instruments in the AMA campaign. So, you get high winds here that can be very damaging. Particularly early in the season, you may get these winds when the mid-level dry air is strong. So these low-level winds and gusts are dramatic in terms of the local meteorology. Here's another dramatic picture. This is again from Francois Guichard. And then when they are carrying a lot of dust and moving over the more arid areas and into the desert, then these are sandstorms or haboobs, as they're known. So, in fact, I can show you some more science now in relation to those. So this is a very nice set of observations from the AMA campaign from an aircraft flight. So the map in the bottom right shows the flight. So it's this line which is going roughly southeast to northwest. So that was the flight and the translate we're looking at here. And you can see in this false color, I think it's a temperature difference image from Meteosat. You can see we're crossing this band here, and this is in fact the intertropical discontinuity or front. I'm sorry, people use both those terms, so unfortunately I'm flipping between ITF and ITD, but they're effectively the same. So the flight goes across that front, and that front is a continental feature. You can see it extending a long way across the continent. But when we see this with the LiDAR, and the LiDAR is detecting aerosol principally. Also, there are a few bits of cloud here which obscure what's below it. But you can see the front. There are also drop zones, I should say, from the aircraft, indicated by the arrows at the top of the panel. So these measure temperature and humidity like a radiosonde and winds. So we can see, in fact, in this potential temperature contours, we can see the very cold air close to the ground. So this is the cold air surging forward, and then the really white, intense region here is dust being lifted at that cold air in this Haboob system. So in fact, the intertropical discontinuity at this stage, which on my global map of Africa, continental map of Africa, that's a line right across the continent. In fact, if we zoom in on that, it comes down to scales of kilometers or less, and it resembles a Haboob or a gravity current. So there's the real collapse of the continental scale down to the scale of hundreds of meters. And so it's we always have to remember that when we're looking at these continental scale maps, what's happening on the ground can be much more complex. Here's just another schematic and how these things relate. In fact, the scale on this schematic at the bottom is much longer, but effectively, when we look at a vertical section through the monsoon, again with the intertropical front, I've tried to line those up. What we're looking at is something much more active in the local scale. And so, as a last point, when just talking about these big climatic maps and our climatic overview, is to remember that there's a lot of variability in the diurnal cycle, and this is something very much characteristic of, well, I guess all tropical, subtropical, continental regions. And semi-arid regions, there's typically a very strong diurnal cycle in the flow. So these are SODAR observations from the same instrument I showed you that being damaged, or the screen was damaged. And so they'll profile each of these up to 600 meters. Each row is 7 days. And you can see every night there is a nocturnal jet, almost every night, developing. So high winds are accelerating down the pressure gradient. During the day, then these winds mix down to the surface, and you get high gusts of winds in the surface, say 9 in the morning quite often. And then later in the day, you get the momentum is mixed out by daytime convective turbulence, and the winds are much lighter. So when we look at these large-scale climatic features, they're not static. They're not just sitting across the continent like a semi-permanent front. They're highly dynamic. They're surging at night, and then being mixed out by day. And in fact, going back to that Hamilton Archbold paper in 1945, they noticed exactly this in the Zone B, that there's a strong variability of winds and thermodynamics over the diurnal cycle. So having given the introduction to, I guess, both the continental climatology and something about what that means on the surface, I just wanted to step back a bit and reflect on, well, what it is special about African meteorology. So there's a few of my own reflections here. I'm sure colleagues will have their opinions too. But I think comparing African meteorology maybe with latitude meteorology, the first thing to say is that the convection is strong relative to synoptic control. So this is partly latitude, that the geostrophic rotating dynamics are relatively weak, and latitude in the sense that the solar heating and the convection is strong. And so the intensity of convection and sometimes organized convection, these squall lines are highly organized, long-lived, means you could argue that the mesoscale is not, well, I've said dominant here, but certainly strong relative to synoptic drivers. And the convection remains somewhat stochastic. So by that, I mean that in a given day, the deep convection can develop somewhat randomly, and it can pop up where it wants to pop up. Synoptic control weighs the dice. Whether we are in a certain synoptic environment tells us the likelihood of convection occurring in different ways, but it doesn't so easily tell us exactly where the convection will develop. In contrast to perhaps a mid-latitude cold front, where we can perhaps nail down the location of convection much more accurately. I'm going to come on to these other points. I guess something I'm not going to talk about at all today, beyond this slide, is the vulnerability of people and infrastructure. So there'll be a lot to say about this, certainly in terms of forecast communication. Only 44% of people on the African continent receive early warnings of severe weather, less than half. There are lots of challenges beyond producing good forecasts, down to communication, right down through the value chain of forecasting. But today, I'm not going to say anything more about that. I will say a little bit more about observations, so I'll come back to those a bit later. So, while talking about what's special about African meteorology, I mean, here's a recent paper that has just appeared, led by Richard Keane. And I think this is kind of a dramatic illustration of that first point I was making about convection being dominant in Africa, or at least more influential, and synoptic effects being less influential. What's shown here is the forecast skill, the fraction skill score, on different scales. So the left column is on a 2-day forecast and averaging to, or aggregating at 126 kilometers. So, the relatively small scale. And the right-hand side is a larger scale aggregation, a longer scale, longer-term forecast. And then the colors here, the orange colors are high skill and the blue colors are low skill. So you can really see this contrast. So in the mid-latitudes in Europe, we are used to getting good 2-day forecasts. People rely on these for decision-making at the scale of a region, of a country. Whereas across Africa, the skill on those scales is much lower from numerical weather prediction models. And then if you look at the sub-seasonal forecast, 11 days, the pattern's reversed. So in Africa, there's much more opportunity for skill. If you average over a large scale, if you aggregate over a large scale, you have much more opportunity for skill on those longer timescales. So I think this is, we've been saying that should be no surprise for meteorologists. We've kind of known that since the theory of Lorentz in the 60s, these kind of patterns. But I think this is a dramatic way of showing how this pans out into the forecast models. And what's found in this paper, really interestingly, is that the new AI-based models, at least the current generation, have almost exactly the same patterns of differences between skill. So I think it remains to see whether AI models in the future will overcome that. But at the moment, they don't seem to. So I have a few reflections on this. I perhaps won't dwell on these remarks here, but I think, just to perhaps reinforce what I've been saying, the patterns of predictability are different in Africa to the patterns in Europe and the global north because of latitude, because of solar heating. We still need numerical weather forecasts. They're necessary for effective forecasting. But in Africa, I think they're not sufficient because they don't have this skill at the small scale. And so to give people good information at the small scale, we need nowcasting. But equally, we have this sub-seasonal, sorry, S2S is jargon, it's sub-seasonal to seasonal forecasting skill. We have potential for that. And so if we can treat things statistically and forecasting statistically, then we can exploit that skill. And there's one physical process mentioned on a previous slide that offers some opportunities for exploiting that skill. We can ask, where does that skill come from on a sub-seasonal scale? And I think the general understanding is it probably comes from land surface and ocean coupling. So there's just an example here of a relatively old paper. There are probably newer ones, indicating how the evolution of sub-seasonal features. What's shown here is a composite propagating vortex associated with the onset of the monsoon in West Africa, and the associated land surface soil moisture patterns alongside that. And so this kind of coupling is becoming well documented in all kinds of scales. And it's this kind of coupling, because the land surface having a slower timescale of behavior, that offers I think, opportunity for effective prediction on these timescales. I just wanted to put this in because I couldn't resist, and this is actually showing the land surface importance at the small scale. I can't resist this because this is one of our research flights in AMA. So Chris Taylor produced this very quickly after the campaign. So you know, on the fly on his laptop, I think. So this triangle that's buzzing around on the left-hand panel is the BAE Research 146 research aircraft. And what you can see on the left-hand side is a large mesoscale convective system developing. On the right-hand side is the preceding surface temperature. So in fact, this system develops on a hotspot, which is in the center of the domain almost, with a wet surface nearby. And a great deal of research, you know, which has gone on following this campaign has really confirmed that statistically and continentally that the development of convective systems is really strongly modulated by the land surface. And this provides an important dynamical feedback between the fast dynamics of the convection and the slower dynamics of the soil moisture. So the conclusion here, I would say, is that including soil moisture in our methods is likely to be fruitful in terms of improving forecasts, and particularly on the small scale where people live. So I think this is the last remarks about what's special about Africa in terms of meteorology and forecasting, and this is a kind of well-known observation that well-known remark that the observational network over large parts of Africa is below what is expected internationally, and those international expectations are based on the needs of numerical weather prediction largely. So the left-hand panel, and I just took these this week, so I just grabbed them from the European Centre site. They're pretty typical. So the left-hand is surface pressure, which of course is a fundamental meteorological variable for making good analyses and forecasts. The right-hand is upper air data from radio sondes. And the red dots here are stations where I think the reporting has been zero over the period. August 25. So you can see a lot of gaps over Africa, and this is well known. And then when it comes to the small scale forecasting services, there are very few radars operating successfully in sub-Saharan Africa. There are some, but very few considering the scale of the continent and the impact of the kind of systems, the rainfall systems that radars would observe. So that's kind of a negative picture, and the same story has been going on really for decades. I could have shown similar slides in 2000 or during AMA, 2006. But I think also I would strike a note of optimism, because I think the world is changing, technology is changing, know-how is changing, communications are evolving, and I don't know. Nobody knows how this will pan out in the future. But here are just two examples of solutions for improving observation. So the top left is the TAMO network. So TAMO has sort of gone independently of the traditional of the weather services, but working in partnership with weather services to produce low-cost systems using new technology, new ideas, new communications, and you can see that there's a really impressive density of stations in some areas. And then the SOF initiative is a way for the global community to, in fact, motivate, incentivize, and finance better observations, and taking a new approach. And effectively, the driver here is that finance follows success at getting data into international databases. So basically improving the statistics on that previous slide. So these are only two examples, but I think there's been a lot of movement in solutions for observations, and we mustn't be too pessimistic as we go forward. So now I wanted to show examples of African synoptic meteorology. This is kind of fun for meteorologists, I think. Just show a few things, and things we've learned particularly from the AMA project and the SWIFT project in recent years. So the elements on this slide are perhaps quite small if you're on a small screen, but this is from the Forecaster's Handbook for West Africa. It's a summary basically for West Africa of the features that we are recommending to be plotted on synoptic maps. So some of those you've seen already in those introductory maps. So and there's a point here that the choice of symbols here may vary from center to center. You may choose a different format for your jets. The tropical easterly jet is the top here, subtropical jets. There are some surface fronts here for the mid-latitude trailing fronts. The dry intrusion boundary, which I'm very keen on, is very interesting, is very small on the screen, unfortunately. But and then going down through African easterly jet, troughs, centers of circulation, anticyclones and depressions. These double arrows, northerly dry bursts and southerly monsoon bursts, are typically showing areas where there's a deep advection of typically moisture in the column, which we see to be linked to significant weather. And then symbols here for ITCZ and or the surface manifestation. So these kind of symbols, and I'll ask the question on the right, what else would we adapt to other parts of the continent? But I think this is a good set, and hopefully I'll show you a couple of examples of how we might use these. So there's a lot said about African easterly waves, and I won't devote much time to that. There are lots of papers on easterly waves. I just wanted to try to offer one way in which we can use our understanding of synoptic dynamics to explain some things about easterly waves. So the diagram here has got some of these idealized schematic symbols. We've got an African easterly wave trough with these double lines. It's in a classical form here, so it tilts against the jet. Then I have some surface flow here, and because the trough is tilting against the jet as well, the trough in the jet level is in the green, so that's the African easterly jet. The trough is here. Then at low levels, we expect the same kind of circulation, perhaps shifted slightly west. So the surface black arrows, this is the schematic of the surface wind with some rotational component near the surface or some positive vorticity. And then there's this deep advection, warm and dry and cool and moist, is shown at mid-levels, sort of lower mid-levels by these red and blue arrows. So hopefully if my animation has worked in the right order, these mid-level advection with the red and blue arrows lead to these anomalies in mid-level humidity. So we expect it to be quite dry ahead of the trough, to the west of the trough at mid-levels. So we have an interesting cocktail here to the west of the trough. We have this dry intrusion moving down, which we know the leading edge of that is commonly where you get organized convection, mesoscale convective systems or squall lines. And then if you look closely at the winds, there's an opposition here between the low-level wind, the southwesterly monsoon, and the mid-level African easterly jet. So we get quite strong shear in this zone. So this is a cocktail, a recipe for organized convection, and that's exactly what we see. So over the years, there used to be some debate about exactly where the convection rainfall was in easterly waves. There was some confusion in this a couple of decades ago, in the 70s and 80s. People were quite mixed up. And that's particularly because easterly waves are also observed in the West Atlantic, and they have different characteristics there. But in fact, there are two maxima in rainfall now observed, and there's a secondary maximum behind the trough. In this area, it's blue, and that's basically because there's a lot of moisture available. So it's a place where it's favourable for deep convection because of the available water. But ahead of the trough is this ideal place for organised systems and these intense squall lines, which develop on the wind shear. So that's just noted here. So that was a kind of cartoon of a classic easterly wave, and it's very easy to get wrapped up in these theoretical models. And there's a lot of things written and said about the classic easterly wave. But in fact, when you look at real cases from day to day, they tend to be much more varied and complex. And in the Forecaster's Handbook, we actually stepped back from saying what is a coherent easterly wave and instead focused on these synoptic elements, which together comprise easterly waves in different environments. So here I'm just going to show an example of the synoptic symbols in a case from the Swift testbed 3. So you can see the dry intrusion here. So the position of this means that the air from the north has come quite a long way south, almost to the Guinea coast in this case. Then we have some other features plotted here. It may not be entirely clear, but some vectors down here showing shear. And now I've drawn a little circle in the center of this high shear zone. The shading here in blue is High Cape. And this is all just to the south of the intertropical discontinuity, which is the railway track here. So there's a location here which looks to be favorable for mesoscale convective systems. And the last thing here, which we plot, because the West African forecasters use it, is the falling pressure, so the 24-hour pressure change. And so there's falling pressure in this region as well. And then the effect of this, unfortunately, the image has moved across, but I've transposed the circle here is where we saw optimum location for mesoscale convective systems. And then the resulting deep convection is on the right-hand side. So I think you can see it here, the complexity of the system. There are lots of cells in the afternoon, in this case, lots of things developing. It's not clear which will really evolve into a major system. But in this case, certainly the evolving score line or MCS was active and favored exactly in the location where we had these synoptic drivers in concert. So there it goes. So the last thing I just wanted to mention in terms of synoptic is, in fact, going back to the very first schematic I had, that the extratropics are really important, even right down to the equator. And drivers from both hemispheres, and I've got examples from each hemisphere here, can almost be dominant in this rather delicate dynamics, these delicate balances of convection and dynamics in the equatorial of the tropical zone of Africa. When there's a strong mid-latitude influence, that can actually take over and increase predictability. So we may have good predictability of a trough in the mid-latitudes, even 7 days, 10 days ahead. And that predictability of the trough confers to predictability over the continent. So the left-hand panel is some work from Neil Ward showing the temperature and then humidity in the lower panel anomalies traced back to trough, which is these latitudes, these longitudes indicated at the bottom, at the top of each panel. So these strong patterns, coherent patterns in a case. And the right-hand side is a schematic from a paper which shows examples of the same kind of control on through mid-latitude southern hemisphere waves, or breaking waves in this case, on the jet, influencing the rainfall onset, in fact, controlling the timing of the rainfall onset in southern Africa. So my final section, the final few minutes, is just to make some reflections, perhaps about the future. I could have prefaced this with the future, but African forecasting across the timescales, going back to this notion that we have different things we want to be doing on the nowcasting, the synoptic, and the subseasonal timescales. And the elephant in the room here is AI forecasting, and this is really bringing a revolution in prediction globally. But it's also, I think, of particular opportunity for African forecasting, as much as anywhere in the world, possibly more than anywhere else in the world. There are just some comments here without illustration, but I think one thing to recognize is that for Africa and tropical Africa, statistical forecasting never really went away in the way that it had done in mid-latitudes. So in the seasonal climate forums, I'm not saying anything about those today, but statistical methods have remained active and valuable throughout. And now we have AI data-based methods, which are maybe a more natural match to the physics which dominate the climate, the stochastic physics of deep convection, than the physics-based models have managed to do. But although these data-driven models are sometimes seen as a black box, in fact, I would say there's an opportunity, in fact, to engage more now with these notions of coherent structures and meteorological structures. I'll give you an example of that in a moment. You'll be able to see these comments here, so I won't say more about these except to dwell on the last one. which is an opportunity, but there's also a threat to the weather services, I think, from AI. This is a wave to be ridden, but certainly a lot more forecasts for Africa are appearing on the internet or elsewhere from private sector companies, largely in the global north. So I'm just going to show 3 timescales now: subseasonal, synoptic, and really illustrate how this may pan out. So on the subseasonal timescale, I think this is a really nice paper on showing how this is not an AI paper. This is statistical, but to me, this is exactly the kind of task which AI should look at. And essentially, the panels here are showing the scale of rainfall predictions at week 3, most of these. The bottom row is week 4. So the rainfall predictions across East Africa. And when it says drivers added, the drivers are global modes of variability, like sea surface temperature patterns. And so this is coming back to this point that if we understand the physics and the drivers, the dynamics, we can include those. And in this case, it was a regression. So a relatively simple statistical approach increases the skill. So our meteorological understanding enables us to increase the skill of a subseasonal forecast. And this, as I said, is exactly the kind of task that AI models ought to thrive at. On the synoptic timescale, another recent paper, 2024 here, showing how effectively a post-processing of European centre forecasts, and that's the best in the lower 2 panels, a convolution neural network, and the easy UQ here is a UNet, I think, and a hybrid model. Both have much higher skill than the raw forecasts. And then right down in the shortest timescale, something close to my own heart, is the nowcasting problem. So the images on the right show an example of nowcasting using the classical NWCSAF. That's the EUMETSAT standard product. There's a major score line here moving across Senegal. The top panel is the retrievals, so effectively observations of the rainfall, convective rain rate. And the lower panel is the 90-minute nowcast at the same time. And because this is a big system which is moving quite steadily over many hours, nowcasting over 90 minutes or even 2 or 3 or 4 hours can be relatively accurate. And this is doing what human beings do. A human being sees this storm moving, and the human forecaster will give warnings to people in advance of that storm. Nowcasting can automate that process. It can give timings, and using AI, we should be able to get even deeper information about the growth and decay of the system. So there's a plug here for our FASTER project. We are putting these products onto an API and an app. So these are freely available across Africa. Please do get in touch if you want to work with us on this, because I think the potential of nowcasting products right across Africa is tremendous. So that brings me to my conclusions. I hope I've managed to do some justice to this enormous subject. The points I wanted to make, I mean, that there are, although Africa is an extremely diverse continent, of course, that there are characteristics of the meteorology and climate of this region which are unifying. And the AI revolution is I think, here for Africa, and it offers optimism, I think, to overcome some of the challenges that have been around for decades. And my final point is, I think AI models should encourage us to take even greater concern of dynamics, modes, and patterns, because in fact AI models are able to make quantitative use of that understanding, those patterns, for forecasting. So with that, I'll conclude. Thank you.
Brilliant. Thanks, Doug. Switch my camera on. So yeah, great. I thought that was an excellent overview. As you say, a lot of ground covered there, but I think that gives us a really good overview of both the climatology of Africa, but the complexities really across the continent. So I'm going to move now to our 2 responders. I'm first going to invite Marianne, who is the Programme Manager at the WMO Regional Office for Africa. So Marianne, can you kind of, I guess, put this into context of, I think certainly some of the elements of that Doug's touched on, particularly in your role working in Africa?
Thank you. Thanks a lot, Liz, for the invitation and the opportunity to contribute to this important masterclass on African meteorology and forecasting. Thanks, Doug, also for your brilliant presentation, trying to cover this complex topic in only 40 minutes, 45 minutes. And I think that this understanding of the dynamics and physics of the tropical meteorology has really led to the improvement of forecasting in Africa. So over the years, forecasting in Africa has really tremendously improved. And the skills of the numerical weather predictions, the climate models have improved due to the improved physics, as I just said, the higher computational facilities, better satellite data, was improved temporal and spatial resolution. So African have gained much more expertise, and more forecasters have higher university degrees these days, and they're attending competency courses, on-the-job training, participating in international research projects with institutions from the more advanced countries, like the SWIFT that Doug just mentioned, so that we are getting information from the forecasting techniques down to forecasters. So getting academia working close to the operational forecasters, so getting information, latest up-to-date information on forecasting to forecasters. So this has really improved the forecasting in Africa. Another key factor is the quality management system that was imposed by ICAO. So because of that, you have many more trained and skilled forecasters, and this has contributed to raising the profile of aeronautical forecasters and other forecasters. Although this has really improved, there is still significant gaps, I would say, and challenges. Some of these challenges are being the result of the national med services in Africa being really underfunded. There is limited observational infrastructure. Doug has just touched on it. Weather stations are quite sparse. Many regions, especially those in the sub-Saharan Africa, lack ground-based observation station, leading to low data density and gaps in the data. The equipment are aging. In the existing infrastructure is often outdated, non-functional, and poorly maintained. So this will end up having a big historical data gaps. The data gaps are either incomplete or inconsistent. So many countries lack long-term, high-quality historical climate data records due to political instability, funding cuts, or lack of digitization. I think everything is related to financial resources. And these data are really needed for many applications, seasonal to seasonal forecasting and climate modeling, as well as nowcasting. This is needed. And Doug has touched on it, the inadequate radar and satellite coverage. This limits the ability to monitor severe weather systems in real time. Also, in partnership with EUMETSAT, and because of the WMO Unified Policy Data, African Met have access to a significant set of data, but not to the highest resolution. Yeah. There is also this limited access to the global data set. There are challenges in internet bandwidths, the infrastructure that make it difficult for National Med Service to download and process large data sets, including the full set of Meteosat second generation. Although there can have access to some limited data access, but if you have a very high internet speed, you can access the full set of data and really make good use, optimum use of this satellite data. On top of these data issues, there are still some technical and capacity constraints. The limitation to have those good forecasting capabilities and the dependency on global and regional models. Many national med services have insufficient human and technical resources. National med services are understaffed, so they don't have enough forecasters to operate a 24-hour, 7-day service. And this is aggravated with the brain drain, how to retain staff that have already been capacitated and got a certain level of expertise. This is an issue. So you will have couple of experts at National Med Services. On top of that, you have the limited technical capacity on computational infrastructure, high performance computer to access or how to access the cloud services, high-speed internet access to high-resolution boundary data, model data to run high-resolution model or interpret model data. Training is also limited. Forecasting staff often lack opportunities for ongoing professional development in new tools, techniques, and technologies. This is often done through only projects, which often train 1 or 2 staff who may even leave soon after. So this is an issue. And there is not a critical mass of experts, as I said. 1 or 2 staff, when they leave, you are in trouble. But these challenges really undermine the quality of forecasting and nowcasting. The other challenge I need to mention is to switch to impact-based forecasting. That this is switching from forecasting the weather parameters, what the weather will be, to what the impact will be. We have the technical guidelines developed by WMO. This is available, but this is not enough. We need the data. You need to get data on the risk, on the vulnerability, on the socioeconomic, and also collaborate with the other sectors so that you can have this impact-based forecasting really going operational. And I think we have really a lot to do in this area. I will stop with these challenges because there are quite a many, but we have also some opportunities.
No, thanks, Marianne.
With the upcoming project like the Space for Early Warning. This is an EU project supporting the UN Early Warning for All initiative. And this will support the capacity development in nowcasting and impact-based forecasting. Although the observational data will still remain an issue. This will be training on technical aspect, but you need the data. But some people will tell me, but Doug has mentioned it, that we have SOF, Systematic Observation Financing Facility, supporting the LDC and SEEDs to be compliant with the Global Basic Observing Network, the GBON. This is a fantastic initiative, I would say, but it supports more the global numerical weather prediction. More data are needed at national level and subnational level for the purpose of nowcasting and many other applications. Other opportunities are the private sector, AI, but these are opportunities, but they can turn into a problem as well, because the private sector may be turning to compete with these national med services. But they can support still the strengthening and the modernization of the observational network if national med services can have a strong, clear win-win partnership through the establishment of regulatory framework. And this is well encouraged by WMO through the Geneva Declaration. Artificial intelligence and machine learning, Doug has touched a little bit on it. Of course, it offers a good opportunity to improve forecasting at lower cost, but as it requires less computational facilities. But again, some capacity development are needed. You need a good data set that will be needed to train the AI models. some countries in Africa and regional climate centers have started some pilot project, but let us see the outcome and more importantly, ensure that this is well regulated to avoid this big chaos of competing with this really underfunded, under-resourced national med services. So I will stop there to give my colleague an opportunity to speak. Thank you so much for the opportunity. Over to you, Liz.
Great, thanks, Marianne. I think you cover, well, obviously highlighting the improvement in forecasting, but then, as you say, a range of limitations and challenges, but also opportunities. And I'd like to come back to some of these when we get into the Q&A, if I can. I think that would be good to take a deeper dive. But I'm just going to move now to Lawal, who is climate change thematic expert at the African Centre of Meteorological Applications for Development. For your thoughts, Lawal.
Thank you, Liz. Thank you, Doug. That was a very beautiful presentation there. And I will thank Marianne as well. She has illustrated most of the problems and the positive aspects that the National Med Service are encountering. Actually, while they were having some problems that are well acknowledged, they made some improvements as well. For example, in the area of climate information services, in the recent past, I think most National Med Service in Africa are restricted to short-range forecasts, 1 to 3 or 4, 5 days, and then maybe an outlook in the medium range of 10 days, an outlook. But with the advent of S2S, sub-seasonal to seasonal climate forecasts, it enables most of the National Med Service to extend their production pipeline of short-range forecast timescale beyond the medium range, such that the medium range forecast timescale can also be fed into existing tools for applying short-range forecast. So this assisted in mitigating the risk of sub-seasonal climate variability on socioeconomic activities within the complex. So, and with this, they were able to collaborate and open communication channels between forecast producers and forecast users that we normally call stakeholders. So, and this enhanced the development of user-tailored impact-based forecasts. So, but this has its own problem too. Even though there is an increased trust in the users of the forecast, well, the problem lies in the computational aspect of meteorology. Most NMS just go to some sites, NOAA, Meteo France, ECNWF, and download charts. So they are still incompetent in computational aspect of meteorology, that is using raw data to generate their tailor-made or user-tailored impact-based forecasts. So, but with some of the projects, as said by Marianne, some of these projects tried as much as possible to help in this direction. But as soon as the project ends, we are back to square one or maybe square zero. And most of these young meteorologists, I think we have brain drain as well, bedeviling the continent. So many things. And I believe maybe little by little, the problem are being solved through collaboration and assistance from our friends beyond the shore of Africa. Marian has said most of the things I would like to say, so there is no need for repetition. Thank you very much.
Brilliant. Thanks, Lowell. Okay, we're going to move into the Q&A. So if there are any questions for Doug or for our two responders, it would be good to try and get some questions that get all three of them involved, I think, as well. But there are a few questions in the Q&A, but please do add any more that you'd like to ask. So I'm going to go to these questions first, mainly for Doug, I guess, linking to the presentation. So the first one is, what is the source of dry air in mid-levels? Is it cold surges from mid-latitudes?
I think there are probably a number of answers to that, depending on the circumstances. So I think cold surges from mid-latitudes could provide this kind of flow, perhaps with air descending from mid-latitudes, and again possibly associated with a mobile mid-latitude trough. But I think you also can get dry intrusions associated with the local dynamics to do with an African easterly wave, with an active vortex. So an active vortex at 700 millibars or so, 650, 700, can advect dry air around its western flank. I think it's certainly interesting to do more work on that question. People are actively trying to understand these internal dynamics of African easterly waves, because it's and they have an effect on tropical cyclone genesis as they move over the ocean as well. Because this very dry air, maybe dusty air, also can impede the development of tropical cyclones. So I think there's a lot more to be learned about it too.
Great. So we have a question about hydrological cycles. How do the extreme hydrological cycles across the continent affect the convective systems, both in an east-west but a north-south axis?
Yeah, that's a good question. I think that there's quite a lot that can be said about that, I think. And I suppose it depends to some extent what's meant by extreme there. To some ways, you could say that the patterns we see over Africa are more intense than what we see elsewhere in other continents. And by that, for example, the contrast between a wet surface and a dry surface over semi-arid regions like the Sahel, but also other regions. After it's rained, you get a really dramatic change in the surface properties. So where it's rained, you get evaporation, a much cooler surface. Only a kilometre away, where there's no rain, you can have a very dry conditions with the opposite behaviour. So that's a very dramatic and extreme gradient. And then we're learning a lot more about how it's a really favourable area over that hotspot to generate new storms or to modulate storms that move in. So that kind of behaviour would be the physics of that the same all over. We're seeing that kind of behaviour in China as well, but in any kind of semi-arid region. But if we're talking then about extremes in terms of hydrological extremes within Africa, then I think probably the same. You could say something similar in that the most extreme storms also feed on these gradients. So we see evidence of the most extreme score lines and MCSs really intensifying when they come over a land surface feature which is favourable. Typically a hot spot, but with a supply of moisture from somewhere. And that combination is perfect. So there's some evidence that actually over the climate change record, since we've had Meteosat, perhaps 40 years now, that those storms have been intensifying, and maybe with this feedback contributing to it. And the same behaviour is seen, as I say, in any part of the continent where you have those physical conditions, the semi-arid surface.
Great. So we've got a question that looks more at the Horn of Africa. So which would be relevant large-scale patterns and relevant variables for subseasonal to seasonal forecasting for the Horn of Africa?
Well, I can give my answer. Lowell is also somebody who would have some interest in this subseasonal forecasting. But I mean, certainly in that study of that I showed, I think that the variables which are used and the sea surface temperature relationships, particularly in the Indian Ocean, so the Indian Ocean dipole, or in general the patterns of sea surface temperatures in the Indian Ocean are a strong modulator of the patterns of rainfall over the continent. And typically, actually, a warm anomaly over the ocean tends to propagate inland. So a warm anomaly over the ocean giving intensified rainfall, and then the same pattern propagating towards the west over land. So those patterns, whether they're suppressed or active, translate over the land. But then relationships further afield could also be important. So the tropical wave modes like Madden-Julian oscillation or the wave modes like Kelvin waves can also modulate the rainfall in that region. And I think we've got more to discover here. One of the things about AI is it can discover patterns unsupervised. Mm-hmm. So I think that's also an interesting question. But maybe I think, Lawal, this is your research expertise, so maybe you'd have something to say.
Lawal, do you want to come back at that or add to that?
Yeah, well, when we talk about S2S, S2S has really done great performance over Africa. Well, as the saying goes, there is no perfect model, but with a great number of example members, it has given us opportunity to do probabilistic forecasting, which in the past was very hard. So with great number of example members, we have been able to be doing this probabilistic forecasting, and they have been performing creditably over the continent. So like I said earlier, the greatest challenge facing that is inability to use the raw data sets by some NMHS, by some National Met Service. So because most of their meteorologists are not all that versatile in computer programming or scripting in a Unix or Linux environment. So I believe if most NMHS look into this direction, the future is brighter than present. Thank you.
Thanks. So there's a question about AI, and I'd like to hear from the three of you if possible. So just thinking about the best strategy across Africa to maximise the AI revolution to address the forecasting challenges. And we heard many challenges, as Marianne listed. The question from Michael says, I understand a few countries are trying some pilot projects, but what would be the best strategies to support these initiatives? So I don't know, Doug, do you want to, because you touched on AI, some of the examples of how AI is being used, both in AI models, but also in the kind of post-processing and how it can be taken for more application use. And then I can come to Marianne and Lawal.
Yeah, it's a really good question. And there are a lot of dimensions to this, clearly. And I said something about it. Marianne said some other things. I think something that's really fascinating about the AI models is they change the relationship with data, with observations. So they use observations differently. They're very hungry for masses of observations for training, and particularly for localization, so retraining of models and fine-tuning them for a local application. So I wonder, in an optimistic world, that actually this will increase the local value of observations. At the moment, the value of observations is for global numerical weather prediction. And actually the marginal benefit, if one country stops producing, releasing observations, the global forecasts are not impacted massively, from one observation missing. But collectively, when many countries stop doing it, then that's a massive problem. But for one country, the marginal difference is not so high. If we think of AI forecasting, if you're tailoring forecasts for your country with your data, those data maybe don't need to leave the country. But all the motivation for the observations is to improve your forecast locally. And the more observations, the better will be your forecast. So in my optimistic world, I would be hopeful that at least in many places, this could really enhance local investment in observations.
Great. Marianne?
Yeah, thank you for the question. I would abandon the same direction as Doug. It will definitely and obviously, I think, improve the forecasting at the local level, but the data is needed. Do we have enough data to train the models? So we need to invest in the data and clear strategies for African AI forecasting. At WMO, we are now discussing it. We've recently have a conference on AI about 2 weeks ago, and upcoming Congress will discuss it and will stand guided by members and our expert. So we don't have yet a clear strategy to go about it, but for sure this need to be regulated, and our national med services need to be protected. Although there are advantages and potential that AI can have.
Mm-hmm. Great. And Lowell, any thoughts on AI and the use, I guess, for maybe S2S as well?
Well, personally, when it comes to AI, I'm still so skeptical about it. I touch it with a long stick because just for the same reason as earlier indicated by Doug and Miriam, the observation data sets. Because most of these observation data sets they are not error free, and you have to be very good in debugging most of these data sets, make them error free, and there shouldn't be any gap in the data for you to be able to train it if you want to use the AI model. So that is why I'm still very skeptical about its performance. And presently, I believe some NMHS, National Med Service, are already looking into that direction, but just for the same reason, they are yet to be convinced. But I think it's a good development because it will be very good for daily forecasts. Mm-hmm. Because from the little interaction I've had with it, it will be very good for daily forecast, at least to some degree of reliability. So, but we have problem projecting it for seasonal time scale or even beyond that. So, but I believe with serious research, things will be fine. Mm-hmm. Thank you.
Thanks. So let's talk about observations then. I mean, you mentioned it, Doug, a really important part. If we're going to use AI, we need to improve observations or more observations. Could we try? I mean, I guess the shopping list is as many observations as possible, but are there certain areas that I think would give, greater improvements? You mentioned soil moisture, and again, there's a question in the Q&A, about the importance of soil moisture observations and monitoring networks for soil moisture. You mentioned sea surface temperatures. Are we looking at ground observations, so just radar? Are we looking at vertical observations, so you get profiles? Where do you think most of the value is going to come from an observational network?
Again, that's an enormous question. I could probably say a lot of things about that. My opinion is it ought to be moderated as well by the fact that we can quantify these things. So there's a recent paper actually published on the impacts of different observation sets through observational data and denial sets. So for numerical weather prediction models and for AI models now, these questions can be evaluated. So my opinion only counts for so much against those calculations. But I think it's still true that satellite data typically doesn't give us as much information about the boundary layer as we really need in very convective environments. The humidity and temperature are really critical and very sensitive for the stability and the low-level winds, the wind shear for the organization of convection. So in situ observations of those things are really, really important. And we really lack the upper air data. So radio sondes are kind of an old technology, but there isn't much that can compete with that at the moment for giving us that information. There's this enormous lag over the continent. So that's I would say that upper air data, the classic thermodynamics and winds, is really critical. It's not the radiosonde is the only solution for that, but that's really needed. Soil moisture, there are satellites that give soil moisture, periodically, but there are always challenges with every instrument. We can patch those things together with surface temperature data, because we get these very strong contrasts when it rains. And models do that. The European Centre model, has been using nudging in the past, whereby if the temperature drops suddenly, you can nudge your soil moisture because that's probably what's happened. At the risk of going in circles, I think for the sort of the forecasting problem, those are the things I would highlight. It's the in situ measurements in the boundary layer, effectively. Radars are kind of vital, but the challenge is enormous. In terms of technology and know-how, and countries struggle really to run radars. So I think there have always been recommendations say we need more radars in Africa, but there are lots of radars in Africa that have been delivered and supplied and never delivered data and don't deliver data. So it's a massive challenge that shouldn't be ignored. Satellite data can do many things reliably. I think those are the things that I would highlight, really.
So there's a suggestion, and again, maybe Marianne or Lawal might want to, but about using citizen science observations, so getting people on the ground doing local observations, whether objectively or subjectively, whether they could be used both to kind of fill some of the gaps or help to train some of these AI models. I wonder if, are there opportunities to kind of move away from just conventional observations to use, people making observations? Is that something that's been considered and used? I don't know, Marianne, have you any thoughts on that?
I think this is something that we are considering at WMO, and we are editing, reviewing our world integrated prediction system to include those non-classic observational data. So I think this is going to be approved probably in the next Congress. It's been discussed last Executive Council. So all sources of data, as far as we can make good use of it, we're trying to include it now in the observational data set.
Great.
Yeah, if I could give another plug for our FASTER app as well. At the moment, if you have the FASTER app, occasionally it bothers you and asks you what the weather is current locally. So we are accumulating a data set of whether it's sunny or cloudy or raining at each location where people answer that question. So the technology is certainly there, and that's just one way. And we see this around the world, don't we? In other countries where this alternative data sources are being used. So absolutely, I think this is one of the great opportunities at the moment, is the use of new technology and new communications.
Yeah. So there's a question around the brain drain problem. This was mentioned by both of you as responders. Clearly is a present and real problem for nations across Africa. So just interested in hearing suggestions from the responders, I guess, as to what the global community can do to help reduce the loss of skills from, your countries, different parts of the world, where you need it most. Lawal, do you want to go first? Yes, okay. Please.
When it comes to the issue of brain drain, I don't think there are ways to arrest that. The only way to arrest that is for the African National Med Service to buckle up and probably improve their condition of service. You see, all National Med Service in Africa has been controlled by government. So their scientists, their meteorologists, hydrologists, climatologists, all of them are considered as civil servants or public servants. So in as much as the condition of service is nothing to write home about, brain drain will continue. Everybody wants the best. Yeah. So you can't blame somebody that has a very good condition of service attracting the best brain. to their side. So I think that is the only way they can tackle brain drain. Then, apart from improving the condition of service, there has to be provision of essential working tools and a conducive working environment for their scientists. So that is the only way to arrest brain drain. So, for example, I know of some scientists at home or in some Africa doing great work, but to publish their findings or paper becomes problem because of lack of fund. So even the money needed to publish paper is more than the monthly take-home pay of those scientists. So that is the problem we are talking about. So you can't arrest brain drain except at the governmental level. Mm-hmm. If they commit to improve the condition of service, provide conducive working environment, provide essential working tools for their scientists, people will stay. Yeah. Thank you.
Thank you.
I will just add on that. Yeah, right. It is a national issue, very complex. And we have set up the African Conference on Meteorology to try to improve the condition of national med services and try to get them more autonomous so that they can recover costs. If they do so, they'll be able to treat better, offer better environment for their workers. For the global community, I would say most of these brain drain are people who have stayed outside and have lived and have benefited from a better environment and scientific environment. And when they go back home, they don't have it anymore. So if this collaboration could be entertained between where they were, have projects that make them continue to keep their work going, it will improve a little bit. So this collaboration and partnership to keep it up is a very good thing. And I think the University of Leeds through DEX have been doing it with continuing having projects with national med services throughout improving their skills and also while trying to keep these experts at national level. Mm-hmm. Publishing is an issue. I remember, Doug, I never published that paper on orographic triggering. Somebody has put a question on the Q&A. So when I went back, I didn't have any facility to continue finalizing that paper. And after I went through other things and we never published it. So it's good to keep up those collaboration and partnership. It will keep the experts at national level. Thank you so much.
So I guess a question for Lawal and Marianne. So this is about where's the greatest need? Is it for nowcasting and early warnings, or is it more for subseasonal when we're thinking about crop planting, or both?
I would go for both. I would go for both. Yes. Subseasonal, seasonal is very much needed for planning purposes when the nowcasting will save lives and livelihoods. So we need to go on both.
Yeah, I support Marianne. Yeah. I will go for both too. Yeah.
Okay, I'm going to finish with one last question. So, Doug, are there any known or observed climate change behaviour to those weather patterns that that schematic that you gave us at the beginning? Have we seen some changes already? And it asks about whether the use of AI and machine learning on historical data sets. So are there any, could this therefore limit its ability to predict unprecedented events going forward? So any signals that you've seen already, and I guess then how are AI models going to be able to predict the future that hasn't, outside of, I guess, climatology?
Yeah, so two quick answers. I mean, we certainly do have observational evidence of increasing the intensification of extreme storms in West Africa. So exactly those squall lines I was showing, that the most extreme of those have increased through the Meteosat record since 1980. So that's quite a clear signal. I think we published a paper, Chris Taylor's paper, that showed a threefold increase, so 3 times as many. At the same time, more intense storms and longer gaps between them. So basically intensification of the water cycle, drier and wetter. So both those things can be detrimental, increasing the risk. And the other question, I think the answer would be yes. When it comes to projecting extremes in future climate with AI, I think there's still a major challenge of actually figuring out how AI could represent things that are beyond the training data. And we have to be very careful with that. I mean, this remains one of the real important factors about a physics-based model. It could be that physics-informed AI can get around this, and actually an AI which has to obey the equations of physics or some other constraints like the water cycle. But for the time being, I think it's still not clear how that could be done. So the physics-based models are the primary tool.
Way to go. Great. Okay, so we've reached 4:30. I could probably go on. There's a few questions in the Q&A, and apologies to those that I couldn't get to them. But thanks to Doug, thanks to Lawal, thanks to Marianne for an excellent presentation and a really interesting discussion. So in 2 weeks' time, we'll have our third in this series of masterclass focusing on tropical meteorology. We've got Caroline Wainwright, who will be presenting a talk on identifying and forecasting rainfall onset in the tropics. So please do join us for that. If you haven't registered for that, I would encourage you to go and do so. And this has been recorded. I think someone asked about getting hold of the slides, Doug. I don't know if you can see in the Q&A. If you're happy to share slides, please do. But we have recorded the presentation. So that will be available in slower time. But big thank you from me. And thanks to Doug, thanks to Marianne, thanks to Lawal for a stimulating afternoon. Thank you.
Thank you. Bye.
Thanks, Liz. Bye.
Thanks.